So, today we are going to discuss spinning tension. The yarn remains under tension during its journey from the rotor groove to the package, and the tension develops because of the speed with which the yarn rotates within the rotor. The tension affects end breakage rate, but how frequently the yarn is going to break during spinning operation depends upon the magnitude of tension that develops while we are spinning the yarn. The other important fact about the effect of spinning tension is the package density, that is density of the final package, which could be either most of the time it is cheese, or it could be cone also. So, what is the package density? That also depends upon the tension in the yarn while the yarn is traveling from the rotor groove to its destination, that is the package. Now, end breakage rate obviously will affect the productivity, and every breakage has to be replaced by a joint through splicing operation, and therefore, a splice is may sometime lead to a kind of fault in the yarn, because it will never be exactly like the normal yarn, and hence too many breakages means too many splice joints, and these splice joints could be a source of fault in the yarn in some cases. So, nowadays the splicing technique has improved a lot, and most of the splice joints are so good in look that most of the time we will not be able to really make out whether it is a joint portion of the yarn or it is a normal part of the yarn. The tension which is acceptable from the point of view of end breakage rate has to be less than 2 centinewton per tex. That means, depending upon the type of the count of the yarn that I produce. So, if we produce a yarn of, let us say 40 tex, in that case the tension level has to be less than 80 centinewton, and 1 centinewton is close to 1 gram. It has to be less than 80 gram, so that we do not encounter too many breaks. This is general guidelines. The tension profile, if we see, which is shown here, that is starting from the rotor groove to the package, the tension in different part of the yarn along its path are not exactly same, they are different. So, the way the tension is changing from the rotor groove to the package is depicted here, and you can see that winding tension and the spinning tension. Winding tension is fairly constant, whereas spinning tension changes starting from almost 0 at the rotor groove, then it goes up to a level F1 to F2, then at the navel obviously it takes a bend, it takes almost a 90-degree turn, and then moves towards the take up roller. In between we can have a twist top, and the twist top also there could be a slight jump in the tension level. It can go from F2 to F3, the twist top is shown here, and then from F3 as it goes to the beyond the take up roller, here there is a sudden drop in tension, and between the take up roller and the package the tension remains fairly constant, which is close to Fr as has been depicted here. So, Fr and F5 F4 sorry not Fr F4 and F5 are practically same. So, this is how the tension in the yarn is rising from almost 0 at the rotor groove to a level in 2 steps, and then the tension falls depending upon the speed of the take up roller, and then beyond the take up roller the tension really falls a lot, and because we adjust the speed of the take up roller and the package in such a way that the tension at this part or in this zone reduces, and at a certain level of tension we keep winding the yarn. So, this is the picture. So, tension is maximum between twist strap and take up roller, and winding tension is generally much less than the tension that we see before it arrives in the winding zone. So, winding tension is much less than the tension before take up roller. Now, this is the picture of the tension, and obviously, we have to see that what is the role of this tension on breakage. We will come to that gradually. Now, spinning tension has been theoretically modeled by some researchers. So, in one of these work done by Grossberg and Mansour, we see this equation which says that the tension at radius r in the rotor groove the yarn arm exists, and at any point on the yarn arm which could be a distance of small r from the rotor groove, the tension is T0 plus half m omega square r square minus small r square. So, capital R is the radius of the rotor, omega is the rotational speed of rotor, m is the small m is the yarn linear density, and T0 is the tension at the rotor wall. So, this relationship has been shown, but considering the friction at the navel, a better empirical relationship is this one, that is T equal to 0.6 m omega square r square, capital R square. T0 usually is very small. So, sometimes people have neglected also while they are trying to estimate the tension in the yarn, but at the same time as the yarn is moving from the rotor, so the yarn comes into contact with some metallic surfaces, and the trumpet or the navel is one of them. So, whenever the yarn is also not only yarn is rotating, the yarn arm within the rotor is turning at a very high speed. At the same time, there is a movement of the yarn along its own axis towards the package. So, the yarn is in contact with the trumpet of the rotor or the navel of the rotor, and this is in contact, and there is certain amount of pressure which is acting on it, and it is also being withdrawn. So, there is some friction which is happening over there, and the frictional resistance also will add up to the tension. And therefore, it has been shown by some people that a better empirical relationship could be T equal to 0.6 m over a square capital R square. According to Gunther Tromer, in a book which is Rotor Spinning, published by Mayland, it has been shown that the spinning tension has been shown to be 1.4 into 10 to the power minus 13 nr whole square dr square, where what is nr and dr are stated here. Nr is the rotor speed in revolution per minute and dr is the rotor diameter in millimeter. Generally, we express the rotor diameter in millimeter, and the speeds of rotor speed generally expressed in terms of revolution per minute. So, considering the usual units which are practiced or used in the industry, this equation has been stated. So, we can get an idea of this equation, the idea of the tension following these equations. The maximum permissible spinning tension, because we have to avoid too many breakages, we have to see that. We cannot run the machine at a very high speed if my fibers are weak in nature. So, the maximum permissible tension has to be a function of strength, intrinsic strength of the fiber, Fs, and F maximum is 1/10 to 1/15 of fiber strength in centinewton per tex. Such kind, this is the maximum tension which can be used in order to make sure that we do not encounter too many breaks, too many end breaks. So, we can get some idea that if my fiber is not really very strong, we will not be able to run the rotor at a very high speed, because tension will be too much and there will be too much of end breakage. That means, how much rotor speed will be attainable will depend upon the quality of the fiber that we are using. Okay. Now, from here we come back to the tension profile, and the tension at different zones can be shown by this set of equations. From navel to yarn formation point, it reduces to this value. F1 is 0.05 to 0.02 times F2. So, in this zone, F1 with respect to F2, there is a reduction, and how much is the reduction? It is around 0.05 to 0.02 F2. So, if we and it becomes this spinning tension at the takeoff nozzle point. That means, it is here in this zone. Takeoff nozzle, that is basically the navel or trumpet. See, in different books or in different research papers, you may find is written sometimes in trumpet, sometimes navel, sometimes takeoff nozzles, but all meaning basically the same. It is the same element which is placed at the center of the rotor, and the yarn takes a bend and then it moves out from this takeoff nozzle or say or trumpet or navel, whatever we say. So, F2 is the value of this tension here after the navel. So, this is taking care of the friction, the yarn frictional resistance the yarn actually experiences while it is crossing the navel, and there is a bend over there. Then tension is maximum between torque stop and takeoff roller. Here then there is another jump in tension, and what is the F3 value? F3 value is this much, that is F2 into the power mu theta, because the torque stop or the twist trap, sometimes it is called torque stop, or you may also find that people are saying this is as twist trap. The yarn is made to pass over it, and when it comes into contact with it, the yarn is deflected a bit. Because of the deflection, there will be change in tension. So, we all know the Amonton's law. The Amonton's law is used to find out the tension after the twist trap or torque stop. So, before and after, the values can be modeled by using this Amonton's law, and this has been shown to be 1.1 to 1.2 F2 depending upon the actually the deflection angle or the angle of contact between the yarn and this torque stop. After that, it drops after torque stop and or twist trap. This is the value. F4 F5 is only 0.2 times F3. So, whatever is F3, F3 is here, then there is a certain drop of tension here. So, between F4 and F5, the tension level is only 0.2 times what was at the F3 level. So, this is how. So, that means actual winding tension is much less than the tension in the yarn that exists between the torque stop and the takeoff roller. So, this has to be understood that the maximum tension is not really in between the takeoff roller and the package. That is, in the winding zone, tension is not really maximum. Tension is maximum prior to the winding zone. So, even the winding tension may be normal, but still we may encounter too many breaks, because the winding tension may be close to normal, still the tension at the other zones may be quite high, because of not maintaining the parameters at the right level. The friction may coefficient of friction may change because of the wear and tear of the parts with which the yarn is coming into contact, and therefore, the tension value prior to this takeoff roller may be quite high, because maybe the navel is a bit damaged or the torque stop is also a bit damaged. So, the yarn is passing over it at a very high speed, and there is a pressure, there are a lot of friction, a lot of abrasion, lot of wear and tear will be there, and as a result with time there will be change in frictional coefficient and therefore, frictional resistance, and hence tension may change also. Now, we will have take an example of tension calculations. Calculate spinning tension of yarn of 25 ticks spun at a rotor speed of 10 to the power 5 rpm using a rotor of 33 mm diameter. How much tension will develop in a yarn of 25 ticks when the rotor speed is almost 1 lakh rpm and rotor diameter is 33 millimeter. So, you need to know what is the tension. So, straight away we use this equation F equal to 1.4 10 to the power minus 13 n r square and d r square. We have to be careful about the units, and if we substitute the values here, then we can find out what is the tension in centinewton per text first. So, we put the values of rotor speed and rotor diameter, and by doing so we get a figure which is 1.524 centinewton per text. So, that is the tension in per text. So, tension in the yarn we have to multiply by the yarn text. So, by multiplying by the yarn text we get the tension value 38.1 centinewton, and as it was shown earlier that the permissible tension level should be less than 2 centinewton per text, and for 25 text yarn that means my maximal tension can be at the most 25 into 250 centinewton. So, it should be always less than 50 centinewton, and here we are getting a figure 38.1. So, we can hope or we hope that at such a speed and with this diameter we will be able to spin the yarn, because the tension that will develop we expect it to be still less than the permissible tension to avoid too many of end breaks. And this is how we can. So, the calculation part is simple. The other thing we may sometimes need to know is the contact pressure on yarn in the rotor groove. Within the rotor you have a band of fibers which are continuously getting deposited, and part of the band of fibers is also twisted, not the entire band. So, if this is the, we have discussed it earlier, if this is the band of fibers here to here, this zone is called PTE zone, and this band of fibers is here. Gradually the thickness of the band will reduce. So, this band of fibers is experiencing lot of centrifugal force. It is resting in the groove and the rotor is turning at high speed. Therefore, lot of centrifugal force is acting on this band, and therefore, and we have to here the twist has to flow into this band, and as I said the PTE zone, that is peripheral twist extend zone, has to be of certain length, that is it cannot should not be 0, neither it should be too long. So, if the pressure, why we need to know, if the pressure is too much, the torque, the yarn is rotating on its own axis, this torque may not be able to flow into the band of fibers, because the band is resting against the rotor wall, and that too in a place which is looks like it is conical in nature, and there then if we want to drive the torque, we have to overcome the frictional resistance against the rotor wall, and frictional resistance is a function of normal force. So, normal force, centrifugal force is the source of normal force on the band of fibers. So, how much the centrifugal force is m r omega square, very standard formula, and if m is the metric count of yarn, dr is the rotor diameter and rotor speed, then m value is this. If we express the yarn count in metric, then this is the rotor diameter, dr by 2 is the rotor radius, and 10 to the power cube is expressing the radius in terms of meter, and then here is the rotor speed. Omega is the angular speed. So, rotational speed has to be changed into omega value, n has to be changed to omega. So, if we do that, these are the steps shown one after the other, so that it is easy for you to understand. After writing the value of m, r and omega, then we are trying to simplify gradually and we arrive at this figure, this equations now. dr by nm, nr square pi by 60 whole square, 0.2 into the power minus 6, so much centinewton per millimeter. That is the per millimeter, so much centrifugal force is actually, so much pressure is working. Pressure is in terms of force per unit length, not really force per unit area. It is how much force is acting per unit length of the band of fibers which is there in the PT zone. Now, here we have what we have done, this band of fiber close to the yarn formation point has been assumed to be equal to the yarn count. As we know that the band becomes thinner and thinner. So, as we go away from the PT zone, actual mass of the fiber is less and less. So, but close to the yarn formation point, this is the yarn formation point. The yarn mass and the fiber mass is practically same, and therefore, we are replacing it by the yarn mass has been replaced. Sorry, fiber mass has been replaced by the yarn mass. So, from the yarn count we can find out what is the weight of yarn per millimeter or per meter, as the depending upon what are the units you are choosing, and we can find it out, and accordingly we can say this is the value that we will get. And if I want to use the text count, then also we can do it. So, these are the same equations. Now, the yarn count has been chosen in terms of text, and we have also can find out what is the final equation. The unit is centinewton per millimeter. So, contact pressure or contact force in the rotor groove can be worked out. So, what we see here, that what really is important that affects the contact force, the most important factor is this, that is the speed of the rotor. So, the rotor is larger, contact force will increase linearly with the diameter of the rotor. So, bigger rotor means more force on the band of fibers, smaller rotor means in a way less force, but at the same time you have to see what is the rotor speed. With the rise in rotor speed, the contact pressure will rise very fast, because it is proportional to square of rotor speed, and the contact pressure is directly proportional to the count of the yarn. So, if the yarn count is heavy, that is if I going for coarser counts, the contact pressure will be more because fiber mass is more. If I go to bigger diameter rotor under identical conditions, contact pressure will be more, and if we go for higher rotor speeds, then contact pressure will increase very fast. So, many a times what we do that we keep the surface speed of the rotor constant and go for a combination. So, that we use small rotor and run them at higher speed, or we use bigger diameter rotor, run them at a slower speed. So, the surface speed remains same. Sometimes it has been found that a combination of diameter and speed that gives you best spinning stability should be preserved. So, that if you want to change the rotor diameter, either you increase or decrease the speed accordingly, so that the surface speed remains practically same, and you hope that by doing so you will be able to spin the yarn successfully. The stability will improve, so that you will not encounter too many breaks. So, anyway, so these are the different aspects that we learn from here. So, the pressure itself is also important, because too much of pressure will not allow the twist to penetrate into the groove, and there because of this also it can lead to end breakage, because the fiber band in the groove are not getting twisted, because the torque is not in a position to reach the groove. Next, this is the final equations. Another example to find out the contact pressure. From the following data I calculate contact pressure. So, these are basically straightforward substitution based, but one should only be careful about the units, because units sometimes will be given in we will give it to different units in order to know whether you really can change the units from one unit to the other. The conversion factors, this should be clear in your mind. So, from the formula which you already know, we straightway substitute the values of count of yarn, the diameter and the rotor speed, and we get a idea that how much force is acting per millimeter of the millimeter of fiber which is there in the rotor groove. Typically, it is 4.5 centinewton per millimeter. So, the PT zone, let us say is 10 mm. So, that 10 mm band of fiber will be experiencing 10 into 40, 10 into 4.5, almost 45 centinewton of force will be acting on this band of fibers, and accordingly the friction will develop, because ultimately the yarn that exists in the groove, the band of fiber, it has to rotate, and these are the friction points. The yarn may not be circular at this point when the fibers are not really twisted, it may be flattened and it will go like a shape like this. And if it is taking a shape like this, obviously the lot of force which is acting, centrifugal force, lot of friction will be there, and one has to overcome that friction. The torque should be sufficient enough to overcome this friction and twist the band of fibers. This problem is not there in the case of ring spinning. Another example is calculate tension force on a bundle of fiber in the rotor groove from the following data. The data is speed is given, diameter is given, count is given, and PT zone 20 mm is given. So, we are trying to find out how much tension is there. This is centrifugal force. Tension force resulting from friction is 6 centinewton. The mu value has to be given. So, the value of mu is 0.1. Now, we go to the end breakage. On the right hand side, the provisional Worcester data is given in relation to the breaks per 1000 rotor hour for carded yarn count, and what we see here that the breakage frequency is practically independent of yarn count in the case of rotor spinning. That is, as the count becoming finer or coarser, the breakage rate really does not change. That is the Worcester statistics. Now, the end breakage rate, the factors which affect it, first of all is spinning tension, next is raw material quality, sliver quality, average yarn count, delivery speed, and yarn twist. These are the many factors that can affect the end breakage rate. First, we discuss spinning tension. We have already discussed about the spinning tension. These breaks will occur after the yarn has been formed. It is usually between navel and the take-up rollers. The short broken yarn end remains in the rotor groove. So, spinning tension within the rotor, the yarn may break, and between the navel and the take-up roller, if the yarn breaks where the tension is actually maximum, then part of the yarn will be stay back in the rotor. So, if we open the rotor housing or rotor box and check what is there in the rotor, we will see twisted yarn is lying there. That basically means that the breakage has occurred between the navel or the nozzle, take-up nozzle, and the take-up roller, where the actual tension is maximum. So, sometimes the yarn may break there. If it breaks there, part of it goes forward and it goes into the on the package, and the rest part of the yarn will be sucked and it will stay in the rotor groove. So, this will give an indication that actually the breakage is happening between the navel and the take-up roller. The cause of breakage is excessive spinning tension, tension peak due to thick yarn region, embedded trash particles, and presence of weak place in the yarn. So, such kind of breakage could be because of excessive tension, or sometimes that could be tension peak. The average tension may be all right, but tension peak may appear because of thick yarn region, or there could be big trash particles in the rotor. Suddenly mass may increase, and due to that the peak may come. The other thing is the weak places, that especially thin regions in the yarn. In that case also the spinning tension will be overcoming the strength of the yarn in the zone that is between navel and take-up roller, and the yarn will break. high CV and imperfection will cause more such breaks, because high CV and imperfection basically means more weak place in the yarn, and therefore we can expect more breakages. Increase in rotor speed causes disproportionate increase in spinning tension, causing more breakage. So, we have to be very careful about the selection of rotor speed, or if we want to increase the speed, we have to see what is the implication of the increase in rotor speed on end breakage rate. Suddenly, even a 5%, 10% increase in rotor speed may cause a huge increase in end breakage rate. Spinning brakes, these brakes occurs at the peel off zone. So, where actually the twist is flowing a bit into the rotor groove. So, in the peel off zone or the PT zone, the band of fiber is partially twisted, not fully twisted. So, there is a in the PT zone, the fibers are partially twisted, because twist is flowing from the yarn, part of the band of fiber is twisted and the rest of the band is untwisted. It is just a parallel band of fibers. Now, spinning brakes occur in the peel off zone. Continuous spinning is interrupted to obstruction due to obstruction of twist flow. So, the twist flow, if there is obstruction, then this is going to happen. The yarn becomes gradually thinner and the break, that is, the spinning will discontinue. Twist is not flowing properly and you are pulling the yarn out at the same time. So, yarn will be thinner and finally, it will break. And how the twist flow is interrupted? Because of presence of big trace particles in the PT zone and presence of fiber clusters. So, a bundle of fiber may be not opened properly and entering the rotor, and presence of even long fibers can result in this, and crumbled fibers. So, these are the very facts which can affect twist flow. Both excessively low and high rotor speed may cause spinning breaks. If the spinning speed is low, the tension in the yarn will be less and the flow of twist, flow of torque into the band of fiber also will be less. See, how much torque can flow through a twisted yarn depends upon what is the level of tension in the yarn. So, if we do not run the rotor at a reasonable speed, then also we will find that there is a lot of difficulty in spinning the yarn. We are not in a position to spin the yarn. Similarly, too high speed also will cause a lot of breakages, because the spinning tension going extremely high and breaks will be there. So, too low speed is bad, too high speed is also bad. Both will cause interruption into the spinning process, and the reason of interruptions are different. So, there is an optimum range of speed in which we have to work. If we go below that, we will suffer in terms of productivity, breakage will be more. If we go too high, also breakage will be very high. For a given fiber and its quality, the trace which is there, the kind of twist we are using, keeping on so many parameters, there is a range of speeds in which we will be able to work, and going beyond that will make the spinning process very, very difficult. Raw material quality, it is very natural that the fibers are fine fibers, strong fibers, low level of trace, they are always good. especially for cotton, and they have a pronounced effect on breakage rate. Finite fibers means more number of fibers in the yarn cross section. It improves cohesion and strength, and thus breaks will always reduce if we go for fine fibers. More trash in the cotton means more trash in sliver, resulting more breakages. More trash in sliver means more trash in the rotor also. Finally, rotor will be getting choked very quickly because of presence of too much of trash in the sliver, and hence the cleaner sliver is always required. And there are certain norms how much clean this sliver should be, and that also depends on the count of yarn that we want to produce, but those kind of industrial norms are there. Seed coats and bark particles are difficult to remove and are detrimental to smooth spinning process. So, these are very bad for the rotor spinning. Then sliver quality, basically two aspects are there. One is cleanliness of the fiber, the other one is parallelization or orientation of fibers. So, from the cleanliness point of view, the level of trash permissible is stated here. These are basically kind of industry norm, and the other thing is the large trash particles in the rotor can create catastrophic break as it blocks the twist flow. That is very dangerous if it is large size trash particles are present in the sliver. So, that means the size of the trash particle also will matter. The other thing is parallelization of fibers. Parallel fibers in feed sliver lead to more ordered arrangement of fibers in the rotor groove, which will facilitate easy flow of twist along the rotor periphery. This is the reason why we say that in the case of rotor spinning, we have to give at least one passage to the sliver, card sliver, because we need to make the fibers parallel, straight and parallel. We want to orient them. The reason is that though most of this orientation will be disturbed by the time the fibers arrive in the rotor groove, but still part of it will be still maintained. So, there is a good correlation between parallelization of fibers in the sliver and parallelization of fibers in the rotor groove. It has been shown there is some correlation, and because of this parallelization, the end breakage rate actually goes down. When you feed at least one drop from passage given sliver into the rotor spinning, vis-a-vis a card sliver being fed the rotor spinning machine. So, just to avoid too many breakages, we have to give at least one passage of drawing. Two passages also could be better, but at least one passage is always beneficial. Average yarn count, end breakage increases if the average yarn count becomes finer, either due to wrong selection of draft or sliver itself being finer. This may happen in industrial situations, that sometimes the draft may go wrong or the sliver itself has become finer due to some reason during the manufacturing of the sliver itself, maybe because maybe something has gone wrong in the draft selection on the carding machine or draft selection on the draw frame. So, there are many reasons why sometimes average sliver count becomes finer. In that case, the yarn will be finer, and because of the tension and the strength imbalances in the yarn, the breakages could be there. Production speed, higher throughput. The dust and trash accumulation also will be very fast within the rotor. if I want to increase productivity, that basically means I have to feed more fibers per unit time into the rotor groove. As I feed more fibers, I also feed more trash particles in the case of cotton, and therefore, the rotor groove will get clogged very soon with the trash particles. Similarly, if I want to produce a very thicker count, very coarse count yarn. Now, coarse count yarn means I will be feeding more fibers, because I have to draft will be less, and it will also a lot of dust also will be fed simultaneously. So, when you try to produce coarse count yarn, my throughput rate in terms of gram of fiber fed per unit time is going to be more, and therefore, more dust is also being fed, and I can expect quick accumulation of dust within the rotor. And when the dust accumulation goes beyond a certain limit, it will cause a break. To reduce the dust accumulation thickness of the dust accumulation, what we do? We go for bigger diameter rotor in the case of coarser count when you are spinning. So, when we try to spin coarse count yarns, usually the rotor diameter that we choose is much bigger in comparison to when we try to spin finer count yarn, we choose smaller diameter rotor. When we go for coarse count yarn, we go for big diameter rotors. The reason is because of this dust problem. Coarse count, quicker fitting of fibers per unit time, more material is going inside, more dust is also going inside. So, dust accumulation rate is very faster, and once it goes beyond a certain thickness, it will end up a breakage. So, if we spread out the dust over a larger circumference, the rate of increase of thickness of the accumulated dust will be slower. So, the breakage frequency will go down. Therefore, reduction in delivery speed can show a positive effect containing end breaks. So, in case the breaks are too much, we reduce production speed, that has a positive effect. Yarn twist, increase in twist can reduce end breakage. However, increase in true twist for a given rotor speed reduces production. Hence, one can increase the false twist by choosing appropriate navel. So, that is what we generally try to do. So, if we increase the twist, strength may increase a bit, and therefore, the breakage rate may go down, but if we try to increase twist, obviously the production rate will suffer. Generally, twist is adjusted by reducing the delivery speed, not by increasing the rotor speed, because the end breakage rate is very sensitive to the rotor speed, or in the case of ring spinning, to spindle speed. So, generally twist adjustment is done by changing the delivery roller speed. In the case of rotor spinning, the take up roller speed we can say. So, that speed will reduce, and take up roller speed means basically means our production rate will be less. So, the way out is that I generate more false twist. And how do I generate more false twist? By having proper navel. So, you will find that we have already discussed navels are available with different types of grooves, and that can help in generating false twist, and false twist means in the yarn arm the twist will go up. So, the yarn arm will be stronger, and therefore, we may encounter less breaks. This is the reason that we go for generating more false twist. Torque stop is also has a similar effect. Torque stop helps in increasing the availability of twist in the yarn within the rotor by 10 to 15%. that is we are not going to increase the true twist, that is why we use torque stop. The very purpose of using torque stop is that you restrict the flow of twist. Ultimately, the twist in the yarn arm is going to increase because of the torque stop. So, torque stop as well as the navel, both of them have a positive influence in generating in making more twist available in the yarn within the rotor, whereas the twist in the package is not going to change, that will remain same. That will be decided as per the normal the twist relationship, that is rotor speed and delivery speed ratio, that will not going to change. Atmospheric conditions is also important. The different types of atmospheric conditions are stated here. Temperature should be around 23 degree centigrade. If we can maintain it, it is good, and these are the typical relative humidities we should have for different types of fiber. Cotton, we need 60% relative humidity. The humidity affect moisture content in fiber and yarn, which in turn affects fiber to fiber and fiber to metal friction, and thereby it can affect end breakage rate. The optimum is this 65 plus minus 2%. If the humidity is too dry for cotton, there will be a lot of breakage, because cohesion will not be there. Cotton absorb moistures, and due to that the cohesion is better between cotton fibers. Otherwise, the cohesion between cotton fibers will be low if it is kept in a dry atmosphere. Whereas acrylic polyester, this thing will not going to be affected because they do not absorb any moisture. So, there the role of moisture is different, that is to avoid the static electricity generation. For cotton, we make the fibers absorb some moisture, so that there is some cohesion between the fibers, and therefore, the breakage rate can be brought down. It is slightly higher than what is maintained in ring spinning. With that, we close today's session. So, we have learned about the spinning tensions, why the tension varies. The tension is different from starting from the rotor group to the package. The maximum tension is occurring between the navel and the take-up roller. Winding tension is much less than the tension prior to the take-up roller. At the same time, we have to remember that the breakage rate is highly influenced by the spinning tension and also on the quality of fiber that we use, and that means it depends upon the kind of process that we select to prepare this fiber, the level of trash in it, and the relative humidity. The other thing is that we can also bring down the end breakage rate by making more twist available in the yarn arm by having either a navel of appropriate type which generate more force twist, or we can use a torque stop. These are the various means by which we have to make sure that the process runs at the optimum level. Okay, with that we close. Thank you.